In today's lesson, we are going to be looking at multi-step equations. Multi-step equations are equations that have variables on both sides. So we're going to look at how we solve them. It is going to tie a lot into what we've done in the past with the previous lesson on solving 1 and 2 step equations. So if you're still struggling with those, please make sure you go back, take a look at those equations, look at how we solve 1 and 2 step equations, because you will see that come up. Not just in this lesson, but in the other lessons on solving equations. So in our course, our online course, there is a Desmos activity. You could probably search it and find it as well. If you search like Desmos Mega Man multi-step equations, it's a small little interactive activity that can kind of visualize multi-step equations, similar to the Solve Me mobiles, but in a kind of fun video game type way. So we will be doing that in class. If you're at home, you can try searching it, or in our online course, you can get the link to it. But we are always going to tie it back into the mobiles, right? Because I think looking at the mobiles, it's a lot easier to kind of rationalize or kind of work through solving the mobile for the unknown rather than looking at an equation and solving it, right? So if you were to look at this equation or this mobile, because they're equal, and we know that each diamond is 5, our goal is to figure out what is the value of one triangle. And now you might say, well, I have one triangle on one side and one on the other. If I get rid of one on one side, I have to get rid of one on the other. And then I'm left with one triangle is equal to, well, whatever's remaining. In this case, there's 15. So one triangle has to equal 15. And if we go back and check, 15 and 15 is 30. 5, 5, and 5 is 15, plus another 15 is 30 as well. So that does work out. If you're able to solve this mobile, you've just solved a multi-step equation. Now, if we were to represent this in mathematical form, assuming we go back, we can leave the 5s because we know that's given. If I wanted to come up with a mathematical expression, I'm going to have an equal sign to represent the middle. On one side, I have 2 unknowns. So to represent 2 unknowns, I can represent that as 2x. On the other side, I have 15 plus 1x, or the one unknown. So to solve this, we said, well, let's get rid of one unknown on one side. So in other words, I'm going to take away an x. And I also took away an x on the other side. Again, very similar to what we've done in solving equations. What you do to one side, you do to the other. Opposite operations. The x's would cancel out on the one side, and I'd be left with 1x equals 15, or just x equals 15. So that is the solution to my multi-step equation. Now, this was a simpler version of a multi-step equation because it really only took us one step, but the idea of having variables on both sides is a characteristic of multi-step equations. Usually it takes more than one step. This case it didn't, but the concepts that we are looking at is what we're going to be doing throughout this lesson. And the idea is we want to get it, we want to simplify our equation or get it so that the variables are only on one side. So let's look at this one. This one's a little bit more challenging. 3x plus 2 equals 2x minus 4. So this over here is a multi-step equation. We have variables on both sides. Looking at it, it might be a little bit challenging. So let's draw it as a mobile. So 3x, okay, well I can represent that. Maybe I'll do 3 squares. And then plus 2, I'll do a circle. So I'll have one circle equal to 2. The square will equal an unknown. I have my left side, my right side. I have 2 unknowns. So 2 squares minus 4. Right, so to represent negative 4, let's say we have triangles. We'll have 2 of them. So now let's go through and try to solve. So I want to get all my squares on one side. So let's say I get rid of these two, get rid of 2 on this side to balance it out. So I'm left with an unknown, I'm left with 2, and I'm left with -2 and -2. Well, if I get rid of a circle on one side, I have to take away 2 from the other side, or in other words, I have to add in another negative triangle, or a little triangle. Now all I'm left with is 1 square and -6 on the other side, so that means my answer has to be -6. Mathematically, if you were able to go through and solve that puzzle, you could have done the same. You've essentially solved this multi-step equation. Again, if our goal is to isolate for x or get the variable by itself, we need to make sure that we only have the variables on one side. So I need to get either this over here or this over here. Now, either way, it doesn't matter. You might have a preference on where you choose to have your sides. I'm going to cancel out this 2x by subtracting 2x, and I'm going to do the same thing to the other side. So 3x minus 2x is 1x. The plus 2 is still there. The 2x minus 2x cancels each other out, and all that's left is -4. So I did one step, and now I'm down to a two-step equation. 1x plus 2 equals -4. Or you could think of it as just a one-step equation. How do I get rid of that plus 2? Well, I minus 2. Keep things balanced. Do the same thing on the other side. I'm left with x is equal to -6, which is the same answer that I got with the mobile. So if you're stuck with the mathematical form, try converting it into a mobile and see if you can solve it that way, right? Hopefully it helps you kind of through the process and then eventually become more comfortable using the mathematical form, because it can get very challenging depending on the equation, how you convert it into a mobile. So our goal should be to be able to solve these equations mathematically and not just in the mobile form. But if we need to revert to a mobile to kind of help us through that process, that's okay in the beginning. Again, with that angle of can we do it with a mobile or with the mathematical form. Now, two things we want to keep in mind as we go through, right? Still with the opposite operations, right? And the main thing when we're dealing with multi-step equations, we want to get the variables to the same side of the equal sign. Right, so we want to make sure that all our variable terms are on one side of the equal sign. We got to make sure we use opposite operations so I can cancel out variable terms just like I did, or just like I would any other term. And we have to remember collecting like terms. And we'll talk about that when we go through some examples, but we want to make sure that we remember collecting like terms. So we have two multi-step equations that we want to solve for. So right now we have 3x plus 4 equals 2x minus 1. I have x terms on both sides. Right? We have this 2x and this 3x, and it's on opposite sides of the equal sign. I want to get it so that the x terms are on one side only. Now, depending on your preference, you may choose or you may prefer to have the variable term on the left side. So for example, you might prefer to have the x on this side and it equals the value, or you may prefer it to be on this side and it equals the value, or it may not matter to you at all. In these cases, when we're trying to cancel them out on one side, my suggestion would be always move or get rid of the smaller term. So in this case, between the 3x and the 2x, I'm going to choose to cancel out the 2x because it's the smaller term. It's the smaller number. And in the end, when I do that, it's going to kind of try to ensure that I don't have negative numbers. Right? So it's a lot, and we don't really like working with negative numbers. It just adds an extra step. So if I can avoid doing that, I will. And what I mean by that is, I want to cancel out this 2x. I want to get rid of the x's on this side of the equal sign. So in order to get rid of 2x or plus 2x, I have to minus 2x. I'm going to do the same thing from the other side. keep it balanced. Now you might notice that I put this minus 2x right underneath the 3x. And that's because we have to consider like terms, right? I'm still doing the same thing to both sides of the equal sign, right? So if I draw that imaginary line down the middle like we had done before, there's a minus 2x on both sides. I paired it up with the 3x because I can only subtract 2x from the 3x because they're like terms. I can't subtract it from the 4 because 4 and 2x are not like terms. So that's why we have to remember our like terms. So the 2x will cancel out with the negative 2x. On the left side, 3x minus 2x is 1x plus 4 equals, and then we have negative 1 remaining on the right side. Really, I don't need to show that 1 in front of the x, so it's just x plus 4 equals negative 1. So this actually works out to a one-step equation. So I had to get the variables on one side. I now have x plus 4 equals negative 1. We want to cancel out this plus 4 by subtracting 4. Subtract 4 from the other side. One side cancels out, and we're left with x is equal to negative 5. If we went through and did it the other way, if I canceled out, I'll just do this a little bit smaller at the bottom. If I canceled out the 3x, so if I had 3x plus 4 equals 2x minus 1, if I canceled out the 3x, so minus 3x, one side cancels out, I'm left with 4 is equal to negative 1x minus 1. Cancel out the minus 1 by adding 1 to both sides. One side cancels out. I'm then left with 5 is equal to negative 1x. I don't want a negative in front, so I have to divide by negative 1 on both sides. Let me just move this up a bit. And then the negative 1's cancel out on the one side, and I'm left with negative 5 equals x. So I get the same answer, right? Even though I canceled out the minus or the 3x instead of the 2x, there's just that extra step of having to cancel out that negative in front of the x. So it does add a little bit of extra work. Again, if you don't really care which way you go, whether the x is on the one side or the other, or whether you work with negatives or not, then by all means cancel out whichever variable term you'd like. If you prefer not to work with negatives, then I would suggest always trying to cancel out the smaller variable term first. For B, 2x minus 7 equals 5x minus 8. Again, I have variables on both sides. Highlight them just so we kind of have variables on both sides. I want to cancel one of them out on one of the sides to get the variables on one side only. Again, like I said, I'm going to cancel out the smaller term first. So I'm going to get rid of 2x. I'm going to minus 2x. That will cancel out on the one side. Keep it balanced by doing it to the other side. I'll put my dotted line in for that reminder. So I have a minus 2x on both sides of the equal sign. It's balanced. One side will cancel out. We're left with negative 7 is equal to 3x minus 8. Again, I only subtract the 2x from the 5x because of like terms and collecting like terms. Also, another thing, do not forget the sign in front. Right? It doesn't become a positive 7. It stays a minus 7 or a negative 7. So I've canceled out the variables on one side. Now I'm down to a two-step equation. I'm going to cancel out the separate term first, or the non-variable term. So to cancel out minus 8, I'm going to add 8. Add 8 to both sides. One side will cancel out. Negative 7 plus 8 is 1 equals 3x. Now I'm down to a one-step equation. I need to divide both sides by 3 because, again, between the 3 and the x is multiplication. The opposite of multiplication is division. Balance it out by doing the same thing on both sides. One side cancels out. I'm left with 1 over 3 equals x. So that is my solution. So this is an example where it is helpful to understand the steps of how to solve it mathematically, because trying to guess and check or trying to use the mobiles might be difficult when we have an unknown that's a fraction. Right? If the unknown or my variable is a whole number, then it might be easy to guess and check, plug random numbers in, or use the mobiles. But when we end up with fractions, right, as our answer or solution, it can be a little bit more difficult. And that might be the case. We might have answers where our equation, where the value of the variable is a fraction, where it's not a nice number, where it's a decimal. Right? So understanding these steps is important because not every equation is going to work out into a nice value. So for example 2, let's check our solutions. So let's go through that process again of checking our solutions. So we just, as a reminder, we have x is equal to -5 and x is equal to 1/3. So I'm going to go through and check each solution. Remember, that is where we plug it in and check the left side equals the right side. So I'm going to write them separately. You could write them out as one long equation, but sometimes it's easier to do left side and right side separately. So 3x plus 4 and 2x minus 1. I'm going to plug in this solution. So 3 times -5 plus 4, 2 times -5 minus 1. And now it's just a calculation. So -15 plus 4 is -11. -10 minus 1 is -11. Left side equals the right side. That's the right solution. So if we didn't trust our answer, we've just checked and it is the right solution. For B, same idea. Left side, 2x minus 7. Move this down a bit. Right side, 5x minus 8. I'm going to plug 1/3 into for x, so 2 times 1/3 minus 7, 5 times 1/3 minus 8. We have 2 over 3 minus 7. Common denominators, so 2 over 3 minus 21 over 3 gives us -19 over 3. The other one, so 5 over 3 minus 8. Common denominator, we have 5 over 3 minus 24 over 3, which gives us -19 over 3. Left side equals right side. My solution of 1/3 is correct. So again, just a way that you can always check your answer just to see if it's correct. If it's not, if left side doesn't equal right side, then chances are you have to go back and maybe try solving again, or double check your calculations first. Maybe you plugged something wrong in when you did the left side equals right side. But if you double check your calculations and you get the wrong thing, you get that it's not equal, then you have to go back and solve again. So looking at a word problem, the length of a soccer field is 31 meters less than twice the width. The perimeter is 346 meters. Determine the dimensions of the field. So this is where the highlighting is important. So we have some numbers. We have that the perimeter is 346 meters. We have the length of a soccer field is 31 meters less than twice the width. We have the question, determine the dimensions of the field. You could also say that for perimeter, the perimeter is 346, right? So including kind of the context, length of a soccer field is twice the width, and everything else is kind of background. So let's kind of draw a visual to represent this. So I have my soccer field, it's a rectangle. The length of the soccer field is 31 meters, less than twice the width. Well, I don't know what the width is, so I'm going to represent the width with just, we'll call it x. We'll keep it similar to what we've with the variables. You could put any letter you want. You could put W, you could put Q, you could put J, whatever you want. I would avoid maybe putting L because that might get confusing a little bit later. But you can choose whatever letter you'd like. So we have the width is x. For the length of the soccer field, well, we know the length is 31 meters less than twice the width. So how do we represent that mathematically? Well, 31 meters less than twice the width. Less means we have to subtract from twice the width. So twice just means multiplying by 2, so 2x. So that's twice the width. 31 meters less would be to minus 31. So now I have a visual representation of my soccer field with measurements. Remember that the opposite sides of a rectangle are equal, so even though I don't show the measurements on these two blank sides, I do know what they are. The other thing is, the perimeter is 346 meters. So when I should be doing something to solve for the perimeter. So I know P is going to equal 346. That's given to me. And perimeter again is all the sides added up, or the distance around the object. So in this case, I could write out all my sides, 2x minus 31 plus x plus 2x minus 31 plus x. And because that's the perimeter, that has to equal 346. So this looks very similar to one of the collecting like terms questions that we've done before. I can simplify this equation by collecting my like terms. I have x terms, and I have numbers. So I can go through and collect those like terms. 2x plus x plus 2x plus x is 6x. Negative 31 minus 31 is negative 62. And that has to equal 346. So we went from a multi-step equation to a two-step equation. So two-step equations are important because we are going to we're going to simplify our more complex equations and eventually come down to a two-step equation. I want to cancel out the non-variable term, so this minus 62, by adding 62. Add 62 to both sides. One side cancels out. 6x is equal to 346 plus 62, which is 408. Now I'm down to a one-step equation. I want to cancel out the 6x, or the 6, not the x, I want the x. I'm going to cancel out the 6 by dividing by 6. Do that to both sides. One side, the 6's cancel out. I'm left with x is equal to 408 divided by 6, which is 68. So that tells me that x is equal to 68 meters. Am I done? Well, we have solved the equation, but however, we have to go back and say, okay, well, what was the question? And we highlighted it, so that helps. The question was, determine the dimensions of the field. Dimensions means, what is the length and what is the width? So we want the actual measurements of the field. We did need to find x, so we didn't do this for no reason. The width we have is x. So in our case, the width is just going to be 68 meters. For the length, it's 2x minus 31, or 31 meters less than twice the width. So that means it's 2 times 68 minus 31 is equal to 105 meters. So therefore, the length is 105 meters and the width is 68 meters. So those are my dimensions of this field. So we had to create an equation, solve it, and then use that answer to substitute back into our dimensions or our expressions that we came up with to finally answer the question. Example 4, this last example, another word problem. Two triangles below, or the two triangles below, have the same perimeter. Could we use the information above to determine the value of x? So this one's a little bit tricky, but let's see what it's saying. Right? Could we use the information above to determine the value of x? So it's basically asking us, can we find the value of x? It's also saying that the two triangles below have the same perimeter. So there's no numbers involved that you could highlight all the triangles if you wanted to, each side measurement. There's no other numbers involved. There's no kind of alert words, but there is a keyword of perimeter. So even if we don't know what to do, perimeter is given to us or told or mentioned. So let's try to find the perimeter. The perimeter is we add up all the sides, right? It's the distance around the object. So let's find the perimeter of each triangle. So 2x plus 3x plus 3. Collect my like terms. I have 5x plus 3 is the perimeter of this one triangle. Let's do the same thing for our other triangle. Let's find the distance around. Let's add up all of the sides. Right, so this is just kind of going back to our collecting like terms. X plus 3 plus x plus 4. Collect my x's. There's 3 x's, and then 3 and 4 is 7. So now I have perimeters for both. All right, good. We still haven't found a value for x. We aren't given a perimeter similar to the last question, right? If we were told that the perimeter of one triangle is, say, 100, we could find out what x is. But we aren't. We aren't given that information. Is there anything else that we're given? And if we look at this, there is one other thing that we're given, one other kind of keyword, and that's that we have the same perimeter. I'll use a different color because we used that for numbers. We have the same perimeter. So the same perimeter is a key word that will help us answer this question because it's saying that these two perimeters have to be the same. Or in other words, these two perimeters have to equal each other. So 5x plus 3 has to equal 3x plus 7. Okay, I can solve this actually. This is a multi-step equation. These are similar to what we just kind of did. I'm going to cancel out the variable on one side and I'm going to choose the smaller variable. So I'm going to minus 3x from both sides. One side will cancel out. I'm left with 2x plus 3 equals 7. Oh, I have a two-step equation. I know how to solve this. Cancel out the non-variable term. So minus 3, do that to both sides. One side cancels out. I'm left with 2x equals 4. Oh, I'm down to a one-step equation now. I can solve that. Divide both sides by 2. One side cancels out. And I'm left with x is equal to 2. So that is my final answer. I have that x is equal to 2. I could go and plug that back in and see, do I have the same perimeter? And if I wanted to, I could plug that back in. It's not asking for that, but let's do that anyways, just to kind of check. So P equals 3 times 2 plus 7. We get 6 plus 7, we get 13. On the other side, P is equal to 5 times 2 plus 3, which is equal to 10 plus 3, which is equal to 13. So when x is 2, the perimeters on both sides, or for both triangles, equals 13, which means they have the same perimeter, which means this value of x works. This is my solution. So with multi-step equations, it's just basically taking up the complexity up a little bit, right? We could have variables on both sides, or we could have more than one variable term. Our goal is to collect all the variables to one side of the equal sign, right? We talked about, in general, I would suggest canceling out the smaller variable term on the one side. It makes it easier. You deal with less negative numbers. And then you kind of work through and simplify, going through the same process with your two-step and one-step equations, that idea of opposite operations and balancing. Right? So this is one of the concepts where knowing the basics is going to be very helpful as you go through and get into more complex examples. And this is one of those kind of concepts that you will always see in math, solving equations, right? Trying to rearrange, right? You will always come across that in math. So just make sure if you have struggles, you're going back and doing some practice, really do the practice, or go back and review some of the previous lessons in the unit.